Welcome back. So now finishing up the aerodynamic portion of chapter 3, we're going to talk about supersonic flows. And at first, if you've seen when a particle or an object is going faster than the speed of sound, you generate a shock wave that's going off of that. Okay? And that shock wave's got an angle associated with it. And the angle we usually write as mu. And we have that the sine of mu is 1 over the Mach angle. Okay, so that's a fairly useful relation. Now, we're going to find another way that Kuchemann likes to show this, which is already leading towards things called waveriders, which I'm going to draw and try and do this in different colors, advantage of color versus a black and white textbook. I'm not about to draw a flow over a wedge, but just imagine you had some vehicle that is sitting here, and this vehicle had span S and length L, and this angle, okay, if we wanted to then write that, would be cotangent of mu, and that's equal to Mach squared minus 1 and the square root of that. We're going to define that as beta, and such that in a vehicle here that's actually, think of a delta wing vehicle that is that big, you actually see that the shock is now sitting on the wing. And so that's going to be a very important relationship for us, is when beta S over L is equal to 1. That'll be the shock is now touching the vehicle. Again, this is not true if there's actually a wedge or a cone that's going to further drive that shock off. I'm not talking about that. I'm talking about just I have a point out there, or I have a spike out there. What is that then doing, and how wide can my vehicle be before I then start disrupting that shock again? Okay, so that's super interesting. And then we also then know, and it doesn't derive, and that's okay. And I've seen it. Now I've seen it been derived over flow over a diamond-shaped airfoil, and so that's certainly interesting to go through. And then I've also seen it derived over bodies of revolution. That's also easy to go. A lot of math, but it's still actually old math. There's a really great book from the 1920s that talked about supersonic flows over bodies of revolutions. So this is kind of old stuff that we've known, again, the power of kind of sticking to these analytics. But we know that vehicles that go faster than the speed of sound have wave drag, and it's basically the drag associated with pushing all of those shock waves. Okay, and however many shock waves and the strength of the shock waves. And what's really neat is that the wave drag, CDW, the form I'm writing here is actually a very specific form called the Sears hack, but it's a it's body of revolution, and K0. Here we go. The important thing here is that this is the area. This is the area. V is the volume. Okay, this is volume. And so you actually have a very important relation, which that the drag of the aircraft goes like the volume squared. Now, and yes, over the length of the vehicle to the fourth. But what this now immediately means, like right out of the gun, is that you want to have, if you want to have low drag, you want to have a vehicle with small volume, and you want that volume spread over a really long object. Okay, that's why the Concorde was this really long, skinny thing. It's why, honestly, it's why missiles look long and skinny. We had, I think some reporter asked us a question like, well, hey, your Venus, your first drone just looked like a missile. And the answer is, well, actually, all things that don't need humans with bubble canopies, like all of those things will look like missiles if you're trying to go supersonic, just because of this, right? If you're trying to design a subsonic aircraft, okay, it may look a little bit different, but yeah, anything supersonic that doesn't need a bubble canopy is going to look like a missile, right? It's right. Rockets almost all look the same, right? It's just kind of the flow physics. Flow physics says, and then this can be rewritten here as well. He calls it the volume parameter, so I'll go ahead and write it down. S squared tau squared over L to the fourth. And so the volume parameters, that way it's kind of, it looks like a span and a, in this volume parameter, which is a length over length of the fourth. That way it kind of feels like, 4 lengths, where The volume parameter is defined as that volume over the area times 3/2. Okay. So, and again, I don't really like appreciate that this is the big S, this is the little s span. Okay. I'll really try not to do that when it's super important when I'm doing a long derivation, so you can tell. You can't really tell what's an uppercase S versus lowercase s for me. Okay, so I already mentioned, first kind of real takeaways. Again, volume down, length up. All right, we know that first kind of takeaway. Right? And then the other one here is that it's nice if you then write the full drag equation. Okay, you will have the drag due to friction. You'll have the drag due to vortex lift, IL, again, CL squared times that vortex term. The wave drag, 128 over pi s squared tau squared over L to the fourth. And then another factor, K0. K0, sorry, this is the form for that Sears hack body. K0 greater than 1 would be a non-Sears hack body. Okay. And then 1 over 2 pi, and this is S over L squared, and this is capital S, unfortunately, beta squared CL squared KW. And this is actually lift wave drag. So again, we have this challenge that lift is going to create more drag along the way. It's kind of a pain in the ass. All right. Then the last thing we'll say is we actually can derive pretty simply the pressure coefficient on, this is generically on a flat plate. Okay? So got flow kind of coming out of flat plate, got some shocks, got some other shocks. Okay, in fact, we be particular about this. You actually have expansion shocks here, and a compression shock, and then expansion shock. So kind of expansion waves here, and these are compression waves. Compression waves. All right, so we can actually derive this and see that it is then just tangent of that angle of attack over square root of Mach squared minus 1. And this is interesting because you're going to see this form a lot. This form right here, Mach squared minus 1. And so a lot of times that can be redefined as something else. You're going to see that's the pressure coefficient generically. And so actually both lift and drag are going to drop off due to that. So we can actually solve for lift. That's just 4 sine alpha over that Mach squared minus 1. And then drag is 4 sine alpha to tan alpha Mach squared minus 1, which is basically just CL alpha. And so, lift over drag is going to be basically the cotangent of alpha. So what does it mean? It means for low angle of attack is where your lift over drag gets high. And another thing interesting we'll see, we'll show it later, but this term here, so yes, we're going to want to fly with big wings at low angles of attack. But that term there, you'll also see, when we talk about sweep, you'll also see the lift and drag decline with sweep. But again, you got to pay attention to it because, lift over drag will increase with wing sweep. But what's actually happening is lift is going down, drag is going down faster. So yes, your L over D got better, but it actually you got better at the expense of having bigger wings. And so kind of back before, like we talked about on the last episode where we know high aspect ratio is what we want, same sort of thing. That comes at a cost. So it's not just go maximize it. So same sort of thing here. It won't be just go maximize your wing sweep. We will have other reasons, primarily talking about do you want to be behind the shock or do you want to have that shock attached? Like that'll be more primary of what we decide to do with wing sweep, straight wings or tucked in wings. Okay. And the last one, I actually really appreciate that this early in the chapter he actually did in the book, an introduction into wave riders. Okay, this was pretty cool because wave rider theory is seems pretty complicated. They do not teach this in graduate classes that I'm really that I took. You know, you'd have to get specifically into hypersonic graduate classes before you'd ever talk about wave rider. But I love that this is just this book is on high-speed flight, and so you better cover it because it's important. And then we'll down select what regime we want to play in. But what's happening with the wave rider? So it's in this situation where the shock is really close. So as your speed gets faster, right, the shock gets closer and closer to the vehicle. At some point, it's actually worthwhile to go out and touch it. Okay, and what you can then do is that shock is now on the leading edge of your wings, and you can actually trap a pocket of high pressure air. Now, wave rider theory is neat because we've actually analytically been able to figure out how to do some of this. Now, I'll say that the analytical derived wave rider models are not super useful, and even Kuchemann will get into this a little bit later, but it actually shows that we can derive some of this. So, there's this whole formula behind if I have a wedge, okay, and the flow going directly over top of the wedge is not impacted, right? So this flow didn't even see that the wedge was there. This flow 100% saw the wedge, and I'll go into a different color, and it shocked, right? It formed a shock and shocked down. Okay, such that this flow coming here would hit the shock and then it would deflect a little bit. Okay, so I can actually solve for this flow. In fact, I could have done this as a cone at an angle. We actually have the tools to go do that. And so if I'm doing that, I'm going to come over here and draw what amounts to be this like carrot-looking thing, okay? Because it actually lets you define a vehicle that looks kind of like this, where this is the base of the vehicle, where you can imagine this is the thing that's creating the shock. This is the point up front. And then keeping my shock in red, the shock then sits on the bottom edges of the vehicle, if I could draw it there, and forms in between. And so this region in the middle, I'll put here in orange, is formed high pressure trapped air. And there are a couple different ways of doing it, a couple different forms people have tried out. But this is the generic concept of a wave rider, and it does create extra lift because of that trapped high pressure. So we'll certainly see that configuration later in the book. We'll talk about the regimes where it exists, but I just love how this actually got there. So this felt like a really short introduction given how much theory he jumped into on the kind of the subsonic, and potential flow theory, but not too bad. So shocks create angles. We're actually going to use this beta angle, which is the angle from the front of the vehicle a lot, because we'll be interested in when beta S over L, because that means you should probably think about doing a wave rider. Wave drag goes like volume squared over length of fourth, and so we are absolutely going to want to have our volume go down and our length go up. This immediately goes into fuel selection. Yes, we will all get impressed by, again, hydrogen and its fuel efficiency. It's hard, right? We even did at Venus. We looked at hydrogen. It wasn't pure hydrogen. We looked at it early, and just even that advantage that we thought we had kind of found came really hard to package, and the wave drag was just really high. Okay, so that wave drag is a monster, and then we can actually write down the full drag equation. So we're going to have our standard viscous forces. We'll have the drag due to lift generically. We'll have the wave drag, and then we'll have this lifting wave drag as well. And so that's all kind of part of it. And then just remember as well, the last kind of piece is that there is this kind of Mach compression piece. So your coefficient of lift, whether it's your coefficient of lift or your coefficient of drag, all of them are going to go down as you go into higher Mach number. So we'll see you next time when we talk about propulsion.